Ich begrüße Sie alle recht herzlich zu unserem Tech-Update-Webinar. Wir haben was sehr Interessantes heute, nämlich ScaleFlux. ScaleFlux ist vereinfacht ausgedrückt SSD-Drives, die auf Basis von Micron basieren, mit allerdings einem netten Add-on, nämlich mit einem sogenannten FPGA-Chip. Zeigen dann später noch von ScaleFlux einige interessante Benchmarks, Anwendungsgebiete, wo macht es Sinn, wo kann man das einsetzen, ja, und welchen Profit hat man durch diese Variante. Es verhält sich erstmal im Prinzip genauso wie ein normales Drive, was man kennt, normales NVMe Drive, was gerne im Markt ist, wie Samsung, Micron, Toshiba. Es gibt es im UDO2-Bauformat und natürlich auch als klassisch noch als NVMe-Steckkarte. Das Interessante an ScaleFlux ist, durch den FPGA-Chip, der auf diesem System drauf ist, auf diesem Drive, kann man mit Komprimierung arbeiten. Das sehen wir später dazu auch noch ein paar Slides. Ja, mein Name ist Alexander Tilgner. Ich bin bei der Firma Boston als Engineer tätig und beschäftige mich mit, sage ich mal, allem, was, was im Data Center notwendig ist oder im HPC-Umfeld. Wir haben noch den Mr. Baker hier, ist von ScaleFlux im Marketing tätig und fürs Produktmanagement. Und ja, würde ich sagen, starten wir. Andreas, die nächste Slide, bitte. Danke. Dauert ein bisschen. Hier sehen wir jetzt nochmal die zwei Varianten, die es gibt. Die Serie ist CSD-2000. Manche vielleicht sind schon mal über ScaleFlux drüber gestolpert. Die erste Serie, das war die 1000er Serie. Das ist jetzt ein Jahr her. Als ich das erste Mal gehört habe, dachte ich mir also, was soll man jetzt damit anfangen? Ja, was ist da wirklich jetzt so Besonderes dran? Spätestens beim Einsatz als Storage oder jetzt zum Beispiel auch für Archivspeicher wird man dann sehr schnell erstaunt sein. Diese Komprimierung, die auf diesen NVMe Drive stattfindet, die ist wirklich außergewöhnlich gut implementiert. Also verhält sich anders wie jetzt, sage ich mal, klassischerweise ein WinZip oder ein LZ4, was man vielleicht irgendwo auch noch von ZFS her kennt. Das Ganze macht es im Datenpfad. Das heißt also nahezu ohne merkliche Verzögerung oder Einschränkung in der Datenrate. Wie gesagt, zwei Geschmacksrichtungen sind die Steckkarte, verwendet man halt eher selten. Die meisten kennen das UDO2-Bauformat, was halt eigentlich eher so gängig ist. Andreas, vielleicht mal die nächste Folie, bitte. Sorry, dauert immer ein bisschen. Genau. Hier sehen wir mal kurz den Überblick, wo es genau oder was ist es eigentlich genau, ja. Ich will jetzt gar nicht den neuen Slang hier, Marketing-Buzzword Computational Storage hernehmen. Es ist vereinfacht ausgedrückt eben wirklich Flash Storage mit einer Compute Engine drin, implementiert durch diesen FPGA-Chip. Ich sage mal, interessant ist das auch vor allem für Datenbanksysteme. Das sehen wir dann später auch noch. Das beschleunigt es doch sehr drastisch. Wird man ungefähr so ein Gefühl dafür bekommt. Also das Ganze ist auf Basis von Micron 9200 basiert das mit diesem FPGA-Chip drauf. Man bekommt ungefähr von so einem Drive die Performance von einer Intel Optane und darüber hinaus. Und das ist eigentlich das Erstaunliche daran, wie dieser FPGA durchschlägt im ganzen System. Es ist transparent von der Implementierung her, also läuft gängig unter allen möglichen Linux-Systemen, meldet sich auch im Linux als Block-Device. Zusätzlich bekommt man ein zweites Device, das ist nämlich dann dieser FPGA. Und ja, man muss das jetzt nicht nutzen, man muss nichts programmieren. Das heißt also, man baut die UDO2 ganz normal rein, wie man es jetzt von anderen Laufwerken auch gewohnt ist. Und im Linux lädt man noch ein entsprechendes Kernel-Modul dazu und dann ja, ist man eigentlich ja, von der Performance her und von den Möglichkeiten her ein gutes Stück weiter. Vielleicht mal bitte die nächste Folie, Andreas.
Well, it's JB flipping, so I'm guessing you're saying change the slides.
Ja. Sorry. Ja, hier sieht man es nochmal. Wir haben Compute Networking Storage, was jetzt immer mehr, sage ich mal, zusammenwächst. Viele kennen auch das Thema SmartNICs inzwischen. Ja, ich sage nur Stichwort NVMe over Fabric. Da ist es natürlich auch sehr, sehr interessant für solche Anwendungsszenarien. Next slide, please. Hier sieht man nochmal kurz mal was man jetzt kennt, also was so die Standardarchitektur ist, CPU, FPGA, DRAM und ja, wir haben halt die CPU über einen Controller, ja, spricht dann entsprechend die Drives an. Next, please. Hier ist die neue Architektur von ScaleFlux. Man sieht, der FPGA wandert eigentlich, man könnte den jetzt auch als PCI-Steckkarte natürlich anflanschen, wandert eigentlich in die NVMe-Drives rein. Hat natürlich den netten Charme, dass je mehr Drive ich verwende, skaliere ich automatisch mit diesen FPGA-Chips auch. Die sind natürlich jetzt nicht so leistungsfähig wie jetzt, ich sage mal, die aktuellen Referenzmodelle von Xilinx. Allerdings, ja, ich kein Vieh macht auch Mist. Das heißt also, wenn ich da entsprechend mehrere Drives nehme, steckt da doch schon eine ganz gewaltige Power dahinter. Next slide, please. Ja, deswegen generell jetzt erstmal so von der Vorstellung her, what is Computational Storage Drive, ja, oder CSD ist das Akronym dafür. Einfach ausgedrückt kann man sagen, ist eine Enterprise SSD, ja, PCI Steckkarte oder U.2, kombiniert mit einer Offload Engine, könnte jetzt auch sagen Co-Prozessor, in dem Fall eben ein FPGA und ja, mein Kollege von ScaleFlux wird das jetzt im technischen Detail nochmal weiter ausführen. Okay, let's go.
Okay, yeah, so this is JB Baker, VP of Marketing for ScaleFlux. And, you know, computational storage, people hear that and get concerned that it's complex or challenging to deploy. And while it is complex for us to develop it, we have put it together such that it should be very easy to deploy, and it just plugs into a standard drive bay or standard PCIe slot. And we are combining these computation functions in the drive with all the functions you would think from an ordinary NVMe SSD. So along that, just kind of start off with some of the features. Standard form factors, the U.2 and the half height, half length add-in card, so that small profile PCIe card that plugs in with a x4. Our primary focus with this is to make sure that we are providing low latency, high performance block storage. So that is the number one thing, is that the drive performs similar or better than an NVMe drive. On top of that, what we add is kind of the purple things on this slide, where within the flash management layer or the flash translation layer, FTL, we've developed a variable length as opposed to a fixed length FTL, and that allows us to take advantage of compressing the data and storing all that, and exposing the extra space back to users to store more data on the drive, as well as to derive additional benefits in performance and endurance that we'll go through. The key things that we have integrated in terms of compute engines are the compression decompression engine. So transparently, when you send data to the drive, we are automatically going to compress it, and when you read, we are automatically going to decompress it. There is no active triggering or application modification that has to be made to have the compression decompression work. We're just going to do it. We also do have, as an alternate version of the software, which is one of the benefits with an FPGA, you can do different loads. We have a database accelerator engine where we will, for RocksDB, we can do predicate filtering down in the drive, which reduces data movement and improves performance for MyRocks. We have all of the features you would expect from an enterprise class PCIe SSD with RAID across the NAND, LDPC error correction, power loss data protection, power and temperature throttling to ensure that nothing goes awry. And then on top of those, we do the advanced data management there where we have atomic writes supported. And that is particularly important for databases such as MySQL and MariaDB, which utilize a double write buffer to assure that they don't have any torn pages in the database. And we've got some data to show you there. Capacities, we have 4 and 8 terabyte raw or physical capacities, but we allow you to change the over provisioning. So it's not just that you buy a 3.2 or a 3.84 terabyte drive off of the 4 terabyte. You buy a 4 terabyte drive, you set the over provisioning, and then you can configure the drive in the file system to expose it as larger than its physical capacity because we're doing that data compression. So our 4 terabyte drive could be used as a 6, 8, 10, 12 terabyte drive to store that much data. And that's where you generate the cost savings, is by storing more data per physical gigabyte of NAND. This is basically, it can apply to basically any application. We've got 3 that we'll show you here where we've done significant benchmarking. And then the database queries is specific to MyRocks. So if you have a customer who is using the MyRocks database, then we could discuss the database acceleration as well. So just very high level here to get started. The performance, what we see, and we'll go into details on these, that we can get better performance, higher overall IOPS, higher transactions, and a better latency profile than you can with an ordinary NVMe SSD or with using a different compression solution. And then in terms of cost savings, by storing all of that extra data on the drive, we're able to reduce the cost, the effective cost per gigabyte. And then also there are benefits in the background where doing that compression reduces write amplification, gives us more effective over provisioning in the drive, and all those things result in better endurance, where as you're writing data to the drive instead of the ordinary NVMe SSD writing 2.5 gigabytes or thereabouts per gigabyte of host data that's sent to it, we're going to write just like 1 gigabyte or sometimes less. And then also a key thing here is that the performance of, or the throughput of the compression scales with each SSD that you add. So we are doing that without burdening the CPU and without running into a bottleneck from the CPU. Now, in terms of kind of baseline benchmarking performance, FIO is the standard NVMe or standard SSD benchmarking tool. And for enterprise drives, what we typically are going to look at is what is the sustained random write, a random performance with 4K IOs. And on this chart, what you see is on the left, 100% of those IOs are random read, and on the right is 100% random writes, and it steps through by 10% increments in between. With an ordinary NVMe SSD or SATA or SAS SSD, you're going to see a curve like the gray line there, and that is data from a competing NVMe SSD. Where at 100% random read, the drive performs fantastic, right? We're 600,000-700,000 random read IOPS. But once you mix in the writes into the workload, now the background activity of garbage collection and write amplification start to occur, and the performance drops off very rapidly. So just going from 100% reads to 90% reads and 10% writes, you see that dropped from the 650 range down to under 450,000 IOPS, and it continues to decline all the way to 100% random writes at about 220,000 IOPS. With our drive doing the compression, we get higher effective over provisioning, and that allows us to minimize that garbage collection, minimize the write amplification, and maintain extremely high performance regardless of the mix of reads and writes. So in the area where most applications that we see actually perform, it's kind of in that, 70 to 90% reads. So over here on, kind of in the left-hand part of the chart, but even in that 70 to 90%, we are, over 2x the performance of the competitor. And as I mentioned, that does help us with the endurance and lowers the effective cost per gigabyte. And all this comes without adding CPU overhead and without adding latency. That's a key thing for doing compression, is what I hear from a lot of customers. They like to do compression, but it adds latency and they can't afford that latency penalty. We're not adding latency doing this compression. We actually improve latency. And then here's on the left-hand chart is an example of that latency improvement. And if we have time, I can open up a different deck and blow up the chart. But here in Aerospike is a database that was designed to use Flash. It was designed for very high performance, very low latency, and they have their own benchmarking tool where you run the benchmark for 24 hours, and it's a mix, a 2/3 reads and 1/3 writes mix. And what they're looking for is very consistently low latency. If you have more than 5% of your read transactions exceed 1 millisecond, you fail the test. So in this left-hand chart, what you see in the purple is the percent of outliers that our drive experienced during that 24-hour test. And well less than 1% all the way across the 24-hour test at a pressure level of 360,000 transactions per second. The next best drive here, one of the NVMe drives, was able to complete the test, but they failed. They were consistently running 5 to 6% of the transactions were exceeding that 1 millisecond threshold. And our drive actually can go up to 525,000 transactions per second while still maintaining or while still meeting those latency thresholds. And Aerospike actually just in the last week updated their SSD certification tool web page showing our CSD-2000 as the highest performing U.2, passing their test at 531,000 transactions per second. So they did that testing themselves. So that was Aerospike's own internal testing, certifying and posting that on their website. What we've seen from other U.2 drives is that here in the center chart, the highest transaction rate that they could pass the test was about 220 and about 300,000 transactions per second. So we're here over 1.5 times the maximum performance while meeting those latency thresholds. And then the last thing here, which is for Aerospike users, not kind of the least important piece, but is important for others, is improving the TCO. So being able to store more data on the drive than its physical capacity. So our 4 terabyte drive is going to cost a little bit more than a competitor's 4 terabyte drive, but it's going to cost a lot less than the competitor's 8 terabyte drive. And we've had a customer in China who did this testing and said, geez, with the amount of data that I can store on your drive, I can actually perform my Aerospike deployment with fewer servers. So they didn't just save on the drives, but they were able to save on the entire infrastructure. The second application here, extremely broadly used database, MySQL. The core thing that we hear from customers here is about reduce my cost. I want my performance. I don't want to suffer on performance. I can't afford additional latency, but my data is growing like crazy, and I just want to reduce the cost of deploying that data. I would love to use compression, but everything else I've tried, CPU compression, offload cards has added latency and not allowed me to meet my performance targets. So here with our compression, we're able to do that cost savings, storing significantly more data per drive. We're hearing anywhere from 2 to 1 up to 5 to 1 as very common compression ratios that customers achieve. And then at the same time, while doing that compression and storing the extra data, we are able to achieve lower latency with the benchmarking tools for MySQL, and achieve higher transactions per second anytime there are writes in the workload. And we've got some data that Percona recently published that validates our claims here. And then Postgres is another, a little bit less used database. And here, the key thing really is about cost. This is not necessarily the highest performance database, or the users are not as focused on performance here. It really is about cost. And what we've seen is that data for Postgres is typically highly compressible. And so our drive took a 1.4 terabyte data set here on the left that takes up 1.4 terabytes on an ordinary drive. And we compress it down to just about 400 gigabytes. So about 3 to 1 compression ratio achieved there. And then the thing with performance on Postgres is that you can adjust this setting in Postgres called fill factor, which is what % of every 8K data page is filled with user data. Ordinarily, they set it to 100%, so 100% of the 8K page is user data, 8K of user data, and that is to reduce the storage cost. But if you want to improve performance, you could say set it to 75%, and then you're only filling 6K of every 8K page. With an ordinary drive, that's going to cause your total storage cost to increase, because to store 8K of user data, you're going to need more than 8K of physical space. And that's what we show in this right set of gray bars, fill factor 75 in the left chart, where that 1.4 terabyte data set grew to 1.8 terabytes when you set the fill factor to 75. We compress, and so that empty space that was put into the drive to improve performance, into the database to improve performance, really took up almost no extra space on our drive. So we're still able to achieve all those cost savings while delivering the performance benefits from the lower fill factor that you see in the right-hand chart. And we have application notes and application briefs on each of these with additional details that you can read through that are available on our website. Now, it's not just ScaleFlux saying that we're achieving these things. We are out there testing with customers and testing with industry experts, and they are echoing our performance and cost savings claims. So, and I'll show you a little bit of information from our partners' results here, but the links here go to the presentations or the blog from Percona, where HP did a big test with Aerospike for their Superdome Flex systems, and showed that with the ScaleFlux drive handling the compression, they were able to achieve significantly higher performance. With Percona, they have already published the MySQL results and are working on doing some testing with Postgres, and they're showing significant benefits from utilizing the compression in our drive for MySQL, and I've got a slide on that coming up next. Customers have been testing the drive, and so we've got a web scale customer in the US who's a big MySQL user, and they are saying what I mentioned before: hey, my database is growing, Flash is expensive, I want to do compression, but I can't afford the latency penalty. They plugged in our drives, tested, and said, you need to come over here and explain how we're getting all this compression without adding any latency. So we had to go, we just gave more details on how the drive works and everything, but they're very happy with the performance that they're receiving and seeing that they're going to be able to achieve about 30% reduction in their overall cost while maintaining performance. Alibaba is a big one we've been working with, and they are, again, cost of flash storage and then hybrid transactional analytical processing database performance. With the CSD-2000, they were able to significantly reduce their storage cost and boost their performance an order of magnitude. An independent industry expert over in China also did Postgres testing, and his results, he showed actually higher compression and better performance gain than we showed in our testing. So this one is a little complicated. We got a lot of stuff going on in this chart. So this is from Percona with the testing that they did, and this is published in their white paper and blog. So a little let you know what's going on here. So the gray bar, the dark gray bar is kind of the baseline here. That is an Intel 4600 drive running in the database here. The lighter gray is the performance that was achieved with that same Intel drive when we turned on host compression. So using the CPU to do compression. And what you see is a significant decrease in performance there, up to 50% worse when you turn on host compression. Okay. Now the light blue is utilizing ScaleFlux drive with our built-in compression. So we are compressing the data here and storing more data than the Intel drive. We're actually using a 4.7 terabyte data set, so a data set nearly twice as big as the data set that was run on that same Intel drive. And we've got the same physical capacity. So we're storing more data, we're doing compression, and we're getting 2x the performance. And then the darker blue, the furthest right set of bars there, is utilizing our atomic write feature. So you turn off the double write buffer in MySQL, utilize our compression, and now you get an additional performance gain by eliminating that second write for every piece of data that you're trying to write from the host. And we've got the link to the white paper there at the bottom of the slide, and a link to the blog post from Percona on the prior slide. So I mentioned the HP testing. This is some of the excerpts from Teresa Melvin's keynote speech, where she had about a half-hour presentation going through big data and the challenges with managing big data, and then the benefits of utilizing Aerospike, and then the benefits of utilizing the ScaleFlux CSD-2000 to manage the compression for Aerospike. She had 4 or 3 full slides and about 5 minutes of presentation on ScaleFlux. You do have to register to actually watch the recording of the presentation, but it's free registration. And then the discussion about the ScaleFlux results are near the end, but a couple of key things here. She echoed the same things we're hearing elsewhere. A lot of her accounts want to compress data, but they can't afford the overhead that it causes on the CPU, or they can't afford the latency penalty that comes from using an add-in card. And then utilizing the ScaleFlux drive, the test results were impressive and getting over 2x the performance and an 80% reduction in latency versus utilizing host compression with ordinary NVMe SSDs. Now, going into, I gotta watch time here, why you might want to use compression in the drive as opposed to a different compression option. Well, and I know this is very high level, but I got a little bit more detail. If you're not using any compression, clearly you're not adding any CPU overhead, you're not adding any footprint, any latency, but you're suffering on the cost. If you use, in the second column, if you utilize CPU compression, now you are burdening the CPU. You're not able to scale that throughput as you add drives, and I'll show you why on the next slide. But the CPUs become a bottleneck in terms of your overall performance. It adds latency, it adds power consumption, etc. You could use an offload card, putting a PCIe accelerator card in there. That doesn't burden the CPU. It's going to get you the cost savings from reducing your data footprint. And the performance sort of scales with capacity. You may have to add more than one card to match the performance of your drives, but it's not transparent. It does add latency. You've got extra footprint and extra power associated with that. When you put the compressor right in the drive, everything kind of balances out there. It scales very nicely with the drive. As you add storage, there's no CPU overhead. As I already showed you, we're not adding any latency either. Now, how the CPU becomes a bottleneck here, what we did is we tested with Intel 3.2 gigahertz Xeon cores and said, how much throughput can we get per core? And how many cores does it take to get to the 2 gigabytes per second of compression throughput that we achieve with each and every CSD-2000? And it depends upon what the compression algorithm is. So a very lightweight compressor, LZ4, it took 3 cores to get to that 2 gigabytes per second. Using gzip level 6 on the far right, it took 47 cores. So that's like your entire CPU complex to just get to 2 gigabytes per second. And that can only fill one drive. That's going to match the performance of one drive in your system. So imagine you've got 4, 8, 12, 24 drives in your system. You just can't scale using CPU compression. And then in terms of how much each of these different compression algorithms squeezes the data, what percent of the original size is the final size of the data, the CSD-2000 does very well there. With most databases, the backend has to be 8K or 4K aligned. And so when you do compression on larger blocks, sometimes you lose out on the effective compression, because if I took, for example, let's say I took a 16 kilobyte chunk of data and it compressed down to 9 kilobytes. Well, then it's going to take up 12 kilobytes because I have to write 4 kilobyte chunks to be 4K aligned. So you lost out on some of the actual compressibility of the data. With the CSD-2000, with our variable length FTL, even though the data appears 4K aligned to the database, it doesn't have to be on our drive. And so we're able to take full advantage of that compressibility in the data. So that's where we get to a higher compression ratio than other compression options here. And even if you are doing, say, LZ4 compression on the host, our drive was able to do additional compression on top of that because of those holes that I mentioned where you had to get back to 4K aligned. So we're able to then recapture all of that compressibility in the data. So I think that is about our time. So in summary, the CSD-2000 is a computational storage drive which combines the high performance flash with intelligent compute engines to get to leadership performance and leadership cost per effective gigabyte of flash storage. That's accounting for the compression. And then with that, we're able to reduce the cost of deploying and running big data applications, databases, and your overall flash storage. So, we ask that you consider using the CSD-2000 with your customers. Our team is available to come in and do additional data or additional presentations on the product, answer questions. Our target customer types are going to be end users who have on-prem or are using colo data centers, or even a cloud service provider would be a good target customer. You don't want to use an end customer who is using cloud, because now you're actually selling the drive to the cloud service provider as opposed to the customer. Target applications, as we've shown, enterprise databases, and this is across different vertical markets. So finance, advertising, big data, online e-commerce, travel, etc. Just across verticals, they're using databases. And the other thing we'd ask is just visit our website. We've got a series of little kind of 3 to 5 minute videos talking about different aspects of the product, specific features, why the compression provides additional benefits, so from our chief technologist as well. And then we've got all the data sheets and product briefs, technical papers as well. And then you've got our contact information here for Daniel, who is our sales representative in Europe, and myself for marketing. Okay.
So great, thank you very much, JB. We got a question in from the audience. It's just from the beginning of the webinar. So the question is: have I understood this right? I can have either gzip compressions or DB query acceleration on one single CSD-2000, but not both.
That is correct. Yeah, we use that's a great question. We use a smaller FPGA so that we can stay within, so it can be cost competitive, and also so we can stay within the power envelope of an ordinary of the U.2 drive. So, and I didn't talk about power, but in our testing, what we've seen is that our drive is within 1 or 2 watts of the Intel and Micron U.2 drives. So typically running in that kind of 15 to 17 watt range. If we were to go with a larger FPGA, that would give us more space in there to put multiple functions, multiple compute engines in at the same time. Now we start to get into extremely high cost and more power. So we couldn't fit into that same form factor. So in this generation of product, yes, those are 2 separate loads that you get one or the other. And then in the next generation of product, 2022, we are looking at being able to do many more features all in one chip.
Good, fine. So then we have the next question. Can you talk about future plans on further CSD-2000 applications? I had a chat with Daniel at Storage Forum in Leipzig in November 2019, and he mentioned, for example, erasure coding.
So erasure coding we actually did do in the CSD or the CSS-1000, and that was a little bit different usage model where it's an offload engine plus an SSD. It's not an inline function like the CSD-2000 is for compression and database acceleration. So the erasure coding was doing in the CSS-1000, what you would do is, for example, for Hadoop, you would want to send the data to the CSS-1000, and it could do the compression and the erasure coding to then send the data out to hard drives for permanent storage. So you just use the CSS-1000 as temp storage and doing that erasure coding. But that's not a feature of the CSD-2000. CSD-2000 is all of the compute that's being done on this drive is for the data that's going to reside on the drive, right? You're going to compress on the way in, decompress on the way out. You're going to, for the database acceleration, you're going to do the filtering on the data that's in this drive. Does that make sense?
Okay, yes, it makes sense. The audience confirmed this.
Okay.
Okay, if we do not have much more questions from the audience, I guess we can yeah, finalize or close the webinar right now. Alex, do you want to mention anything?
Yes, I will do this of German. Falls da noch Fragen sind zu diesem, alles was mit ScaleFlux zu tun hat, bitte bei Boston entsprechend einfach eine Anfrage stellen. Wir haben das auch im Lab. Das heißt, ihr könnt es auch testen jederzeit. Wir haben über ScaleFlux wirklich einen sehr, sehr guten Kontakt. Das heißt, wenn Projekte oder Anwendungsfälle, sage ich mal, identifiziert werden, ja, dann können wir auch Proof of Concepts zur Verfügung stellen, auch direkt vor Ort, wenn es sein muss, ja, also nicht nur über Remote, sondern kann man auch selber dann ein bisschen damit rumspielen, sage ich mal. ScaleFlux steht uns da auch wirklich zur Seite bei solchen größeren Proof of Concepts jetzt, wo es, sage ich jetzt mal, wenn es wirklich konkret wird, und der versorgt euch entsprechend dann auch mit entsprechenden Testexemplaren oder Testmustern. Das funktioniert wirklich sehr, sehr gut. Vielleicht noch abschließend zu dem Thema Latenzzeiten. Sicherlich ist einigen bekannt, Intel mit Persistent Memory versucht einen interessanten Ansatz oder auch die NVIDIMs, um eben die Latenzzeiten bei ganz kritischen Applikationen noch weiter nach unten zu drücken. Ist so, wir haben das wirklich rausgemessen, also wir können auch Benchmarks zur Verfügung stellen. Das ist ausnahmsweise mal kein Marketing. Diese 80% weniger Latenzzeit ist wirklich enorm, das muss man wirklich sagen. Das ist schon eine Leistung. Das hätten wir so beim NVMe-Speicher auch nicht für möglich gehalten. Ne? Dadurch öffnet sich halt eine neue Anwendungsmöglichkeit. Ich sag mal, das schließt so die Lücke zwischen diesen Intel Optane DCP-MM-Modulen und klassischen NVMe-Drives, auch was die Compression betrifft. Und die CSD-2000 ist ja nach wie vor noch erhältlich. Also falls es hier eher Richtung Erasure Coding oder sowas geht, kann man das auch derzeit mit beiden Produktserien entsprechend in den Griff kriegen. Stichwort Ceph. Da laufen wir uns gerade Tests. Das ist wirklich erstaunlich, und zwar nicht mit Compression, sondern eben genau über dieses Erasure Coding mit sehr interessanten Ergebnissen. Also wenn da irgendwo Bedarf ist, bitte einfach bei uns einkippen und melden. Vielen Dank.
Okay, gut, dann würde ich sagen, dann beenden wir jetzt das Webinar von unserer Seite aus. Nochmal von der Firma Boston ein ganz, ganz herzliches Dankeschön an alle Teilnehmer, ein herzliches Dankeschön auch an ScaleFlux, die uns hier nochmal tatkräftig unterstützt haben, um dieses Produkt, diese Lösung auch nochmal entsprechend zu positionieren. Und von dem her wünschen wir euch noch einen schönen Restnachmittag, einen schönen guten Morgen noch nach USA zu JP Baker. Thank you very much for your support again. Und somit schließen wir das Webinar und vielen Dank und bleiben Sie gesund in diesen Tagen.
Ciao, servus, bye bye.
Danke.